In the previous video we created this interface, and we used it to create a Kleisli category in which every function had some logging output. In this video we will look more generally at constructions like these with a generic type argument. You can see the writer as a container for some value, and then it has some extra logging information that is attached to that value. In general, these containers with some type argument are often functors. In this video we will look at what that means. Just like we noted last time that there are some similarities between our writer container and the JavaScript promise container, as in both define a Kleisli category, we can also see that a promise or a .NET task or a C++ future is also a functor. Now, it doesn't really contain anything necessarily. It might not be there yet. That is the entire idea of a promise. It promises something that could be in the future. But we can still think about a promise or a task as being a container. And that is the type of container that we are talking about here. Another common example of a container and also a functor in programming is the list. Here is an example of one of the common operations you do on a list, which is mapping the items in that list to some other value. So here we have a list of all numbers from 0 to 10, and we use the function that creates the square of these numbers to map each element in the list to the square of that number. Now, mapping is also one of the defining features of a functor. Let's take a look at what a functor is more categorically. If we have some general list element and a function f that we use to map the elements in that list, we can draw this small category. Let's say the list has elements of type A, so we have an object A in that category, and the function f maps objects of type A to type B. So it goes from A to B, and that is function f. Now what we do with the list is we create a list of some type. So this is the list functor. And a functor maps a category to another category. So here for each object there is a mapped object. This is what we see with list A and list B. So list is itself not really a type. We can also call it a type constructor, which is the common name in Haskell. In other languages it is often referred to as a generic type, but it is not really a type. List is not a set of values. Only if we add another type as an argument to list, so a list of integers or a list of strings, then we have a set of all values. So list here is a type constructor, and we construct two types, list A and list B. Now if we want to have a function that goes from list A to list B, we use that map function that we just saw. So here we write list.map, which is how that is done in F#, which is the language that I use here as an example. We do list.map and then the function that we use to map a single element, so from A to B, which is our function f. Now in category theory we will write that just as listf, so the same functor is used to map objects and functions. But in programming that is usually the type constructor is used to map objects, and the map function of that specific type is used to map functions. So a functor like list is a mapping between two categories. But as you may note, both the types A and B and the types list A and list B are all types. And so they are all part of the same category set. And this is true. That is why we call the list functor sometimes an endofunctor. So this is a functor that works inside a category, so it maps the category onto itself. But in programming, because we are only dealing with types, every functor is really an endofunctor. And the concepts that we talk about also work when you do have multiple categories that you map between. That is why we generally do talk about functors instead of endofunctors. Now, not any container and any map function describe a functor. There are some rules that we have to adhere to, mainly that we need to preserve the structure of the category. This means that if we have two functions f and g in the base category, and we can compose those into a function h, then the mapping of that function h, so f of h, also has to be the composition of the mapped function f and the mapped function g. This is what we mean with preserving the structure. Any functions that you combine in the base category work the same way in the mapped category. The second requirement for preserving structure has to do with the identity arrow. So if we have an identity arrow in the base category on the object A, and we map this object A into another category, then of course in that other category the object f of A also needs to have an identity arrow, because it is a category. But we also need to say that for f to be a functor, that identity function on f of A needs to be the same as what you get when you map the identity function of A. So the identity functions are preserved. So if you have a list and you use the map function to execute the ID function on elements of that list, then that is the same as just running the identity function on that list. The list elements should not change, and thus the list itself should also not change. If we have the rules in place that preserve the structure of the category across mappings, then we can do something interesting. We can apply multiple mappings after each other. So here we have the mapped list category that was obtained by running the list functor on the base category of the objects A and B and the function f. And then on this category we can again use our writer functor. And then we get a writer of a list of A. So as you can see, functors compose. And if you remember from the second video, if we have composition, then there is a pretty good chance that we are looking at a category. And there is of course also an identity functor, just a functor that maps every object to itself and doesn't do anything with functions. So there is actually a category where functors are the arrows between the objects, and thus the objects are categories themselves. This goes to show that the category is indeed a very powerful concept, which can do a lot of work for us. This series is based on the great book Category Theory for Programmers by Bartosz Milewski. You can find links in the description.